Okay, so we are on. Hello, everyone. Welcome to the next session of ISSTA, Numerical Software Analysis and Clone Detection. We have 4 interesting talks coming up. First one will be discovering discrepancies in numeric libraries. Let me point out that this paper has done quite well with artifacts, won a Distinguished Artifact Award, also has artifact evaluated functional, artifact available, artifact evaluated reusable, and Jackson will give the talk. Please go ahead.
All right, can everyone see that okay and hear me?
Yes.
Great. All right, just a moment, please. So, hello everyone, my name is Jackson Vanover. I'm a graduate student at UC Davis, and I'm going to be giving a talk today about my team's work on discovering discrepancies in numerical libraries. So to start, what is a numerical library? So numerical libraries are going to form the building blocks of more complex pieces of numerical software that accomplish tasks from automated manufacturing to simulating physical phenomena, computer vision, so on, so forth. And there are many such numerical libraries encompassing different languages, representing different features. For today's talk, our experiments dealt with 4 in particular. We've got GSL, that's written in C, JMAT, which is written in JavaScript, and SciPy and Python, which are both, or sorry, SciPy and NP-Math, which are both Python libraries. But there are many more. And then numerical software testing in general has some characteristics that I like to go into now. For instance, numerical software can be thought of as a set of discrete numerical algorithms that implement continuous analytical functions. So in other words, we've got these programs that approximate these real mathematical objects. And the reason I bring this up is because of this, the notion of a ground truth in Oracle is particularly pertinent in this domain. However, things like for instance, there's a non-uniformity in dealing with inevitable numerical errors between these libraries. Some of the libraries might choose to propagate nands, or others might raise exceptions. And also, there's an inherent imprecision in the IEEE standard for floating point representations. And both of these things, amongst other things, can sort of combine to muddy the waters a little bit when it comes to determining what is and is not correct. So on that note, I'd like to actually go into an example here. So when we're determining the correctness of a numerical result, let's say we're doing something like this. We have the Python interpreter up, and we are using the NumPy library. We initialize a matrix 1000 by 1000 with all of these elements at 132 and some change. And when we take the mean function, we all have an intuitive idea about what a mean function is doing. And if all of these elements are the same, we know that the result should be that value, 132.00005. And when we get this result, we have identified, we can sort of intuit the fact that this discrete numerical algorithm has diverged from the continuous analytical function that it's implementing. But let's consider another example. It's more complicated. Say, for instance, we're using the anger function as implemented in the JMAT library. And we give it this input, we see this output. And the question is, does this arouse suspicion? Is this erroneous? And this highlights an issue in software testing in general, right, which is the fact that test articles are hard to find. And in this particular domain of numerical testing, one solution that's often used is to use a high precision implementation to approximate that ground truth. But this comes bundled with some downsides, potentially. One being that high precision implementation can actually diverge further from the ground truth due to things like precision specific operations. The execution of that high precision implementation can become prohibitively expensive. And lastly, just raising the precision allocated per variable may not reveal problems that are inherent to the algorithm being used. So we'd like to present an alternative here then, and another strategy. Let's say that we identify a set of what we're going to call function synonyms. These are functions from other libraries, some from the same library, a collection of discrete numerical algorithms that implement the same continuous analytical function. And these are going to form an equivalence class of, this in particular is an equivalence class of the regular cylindrical Bessel function. And when we give that input, again, we see that old output, but now we can observe the fact that there's large discrepancy here. And this indicates that there might be a bug in the JMAT library. Now, this is a technique that's often seen in bug reports to these numerical libraries, sort of confirming suspicious results after the fact. But the motivation for our team was to think about how we could sort of flip the script a little bit and use this in the first place, this sort of automatic, systematic differential testing to uncover bugs. So what would this automated differential tester look like? Well, it's going to take as input source code for the libraries that are being tested, the numerical libraries, and it's going to output a set of discrepancies. And so we're going to peel back this black box and look under the hood a little bit. There are a couple of components that are going to need to be a part of this automated differential tester, one of which is the differential tester itself. It's going to take in a set of equivalence classes of function synonyms and find the points of divergence between those function synonyms. And the key challenge here is going to be identifying which of these discrepancies are in fact meaningful. You know, for some of the reasons that I discussed before, not all discrepancies are going to be indicative of buggy behavior. And then these equivalence classes have to come from somewhere. And this is going to come from a function classifier whose job is to automatically identify function synonyms. And this is non-trivial for a couple of reasons. Documentation can be incomplete or missing entirely. Function names can be misleading. We've observed cases in which functions with the same name are not function synonyms. Functions with different names are in fact function synonyms. So this merits a different approach. And then lastly, we're going to need an extractor to take source code from the libraries and extract the functions that we are concerned with. So it's going to reinforce our testing scope, whatever that might be. And then we need to synthesize drivers to execute those functions, because differential testing is a dynamic form of software testing. And so overall then, what we see here is FPDiff. It is our end-to-end tool for performing automated differential testing on numerical libraries. And we'll go through each of these components now. So to start, signature extraction and driver generation here. This is going to reinforce the scope for our particular experiment, which was special functions. And special functions are things like the gamma function, Bessel functions, and they're widely implemented across numerical libraries. They represent a diverse and complex set of algorithms, and they also have input types and return types that are elementary data types. So they're a popular choice in the numerical testing literature. And so because of that, what we can do is we can, for libraries that have type information, like here we have the header file from GSL, we can just parse these and identify which functions are candidates for our testing and fit in our scope. But consider libraries like the ones written in Python that don't have that type information. And our key insight here is to leverage developer tests to extract function signatures. So here we see an excerpt from a SciPy developer test, and we can see some of those functions there that are targeted for extraction because they are called with those elementary data types. They're candidates for being special functions. And in particular, these ones that are highlighted here and the one on the last slide as well are parts of that equivalence class that we saw in the motivating example here. So these are then going to be, once they're extracted, wrapped in a testing harness for execution. And then they're going to be given to the function classifier. And what this classifier is going to do to discover function synonyms is going to perform multiple evaluations over a series of elementary inputs, which we define to be inputs that are supposed to result in well-defined behavior for these functions, and ultimately generate a characteristic vector. So what that's going to look like, we have a column here of all of our drivers that we've extracted, all our characteristic vectors, and a set of elementary inputs there across the top. And as we evaluate them one at a time, we're going to populate those characteristic vectors. And these characteristic vectors can be thought of as sort of encoding or representing the semantics of that function that generated them. And what's going to happen is function synonyms are going to be those that have identical characteristic vectors. We can see in blue there then a subset of those regular cylindrical Bessel functions that were in the example earlier, and two more that map together because they have identical characteristic vectors and one outlier. And so ultimately we'll have a set of equivalence classes from this, and these will be passed to the differential tester, which, contrary to the function classifier, is going to use a set of adversarial inputs here that are intended to provoke divergence between those function synonyms. And you can have multiple sources for these. And for the sake of time, I won't go into each of these, but they're described further in the paper. You can use whatever source of adversarial inputs you'd like, though, whatever you think might provoke divergence between function synonyms. So as an example then, here we have, again, that equivalence class from the motivating example, and that input, which is in fact a test migration input from GSL. So the GSL developers included this in their tests. And when we evaluate, we see that discrepancy. And then the last thing the differential tester is going to do is it's going to, once it identifies that it's a discrepancy, it's going to categorize it. It'll automatically assign it one of 6 categories, which is one of our main contributions for this work. And I can't go into all of them now for the sake of time. There's a full description in the paper, but suffice to say that they're sort of organized by the characteristics of the discrepancies and their likelihood of representing buggy behavior. And so this is an inaccuracy, which is a category 3 discrepancy. So to go into our evaluation here for each of the components, our extractor and generator achieved an 88.2% recall, which we measured by manually constructing a ground truth set of functions that fit within the testing scope. And we see for GSL and JMAT a 100% recall. That's because those libraries came annotated with type information, so a trivial parsing sufficed. For NPMath and SciPy, however, the Python libraries, incomplete sets of functions there, and their success was highly correlated with the thoroughness of the test code that we parsed. So for instance, for NPMath there, almost all of those functions that we missed weren't in the developer tests to begin with. And then for our function classifier, it discovered 310 mappings between function synonyms with a 95.8% precision, and a 79% recall. And ultimately, this made up 126 equivalence classes of special functions representing 500 such functions across these 4 libraries. These numbers were calculated, again, precision and recall manually. Precision was affected by our choice of elementary inputs. So in a minority of cases, we found that functions that were classified together based on that set of elementary inputs, that range of elementary inputs, would diverge for inputs that were outside of that domain. And then the recall was mostly affected by the capture rate of the extractor. So in other words, a more complete set of signatures coming from the extractor would benefit the recall for the classifier. And then lastly, the evaluation for a differential tester here. We discovered 655 unique numerical discrepancies. These were all categorized automatically by the differential tester. And then based on those categorizations, we could reduce that set to a set of likely buggy discrepancies that were then given over to our team for manual inspection. And on that manual inspection, we discovered 150 of them, almost half represented reportable bugs. And of those then, there were 125 unique bugs, which is to say that some bugs were represented by multiple discrepancies. And all of these have been reported to library maintainers. And at this point, we've seen 30 fixes, 9 have been found to be previously known, and a further 25 have been acknowledged by the developers. And there's a full breakdown in the paper per library and per input source for those who are interested. So the last thing I'd like to do then is go over some 4 case studies of interesting discrepancies discovered by the FPDiff tool. And this first one here is a discrepancy in the equivalence class of Hurwitz zeta functions. And we're seeing a disagreement here on the asymptotic behavior here. So there's a special value input in infinity, and we can see that the JMAT library there is returning a nan when the other libraries are agreeing on this output of 1. And combine this with the fact that the JMAT library elsewhere supports the evaluation of limits of special functions. This resulted in a report and ultimately a fix. And we were also able in our report then to suggest the appropriate behavior based on the consensus that we see here. The second case study is in the equivalence class of polygamma functions. So this input is an inaccuracy-inducing input. So it's found to maximize the relative error between 1 pair of function synonyms. And that's between those first 2, the GSL and the NPMath implementations of the polygamma function. You can look, if you look closely, you can see that numerical discrepancy in about like the 7th or 8th place there. But what's more interesting is that when we then took this input and applied it to the entire equivalence class, we actually observed a second discrepancy that arose between the 2 NPMath implementations of the polygamma function, one of which inexplicably returns a complex number. So this in particular then is a case where a single discrepancy represented multiple bugs, but also a case in which the fix is not so obvious in this case. This is as opposed to this third case study here, which is a discrepancy between factorial implementations. And when we gave this equivalence class a nan, we observed troubling behavior in the SciPy implementation in which a 0 is returned. And anytime you get a number returned from an input that is not a number, that's problematic behavior. And this also resulted in a report and a fix. But what's interesting is that while this fix, while conceptually simple, just include a nan check, the actual implementation of that fix was rather complicated. And there's a link in the paper to the PR thread, but it involved a back and forth between developers, multiple commits, multiple changes, lasting almost a month. So interesting to look at sort of the development process there. Just highlights the fact that even a conceptually trivial fix might involve a non-trivial implementation. And then this last case study here is a discrepancy in the irregular cylindrical Bessel function that we observed happening with a test migration input that came from SciPy. What's interesting about this example is that it is not necessarily indicative of buggy behavior. So the differential tester, when it sees this, is going to label this as categorize it automatically as the lowest priority. And these are the ones that are automatically dropped when we perform that reduction before we look at the set of discrepancies manually. And the reason for that is that this is actually illustrative of, while it's not buggy, illustrative of an important point, which is that there are different implementation choices made by developers. Here we see varying support for this portion of the domain. So GSL and SciPy do not support this portion of the domain. GSL returning a domain error, SciPy returning nans. And then JMAT and MP Math do support this area of the domain and return a complex number as would be expected. So this just highlights, again, that fact that even though there's conceptually this notion of a ground truth, they're all implementing the same continuous analytical function. There are still these choices that have to be made when adapting it to numerical libraries. So in conclusion, what we've done today, and in this paper, we proposed an approach to discovering numerical bugs. And given our implementation as the tool FPDiff, we found that our classifier, utilizing that evaluation over elementary inputs to discover function synonyms, was very successful. We got a 95.8% precision. And we proposed a categorization of numerical discrepancies with a full discussion in the paper. Suffice to say that not all numerical discrepancies are equal. Some are more likely to be representative of buggy behavior. And we found 125 unique bugs. The source code for our tool is available at that hyperlink. There are instructions in the README for extending this tool, including new libraries, so you can build larger consensus, larger equivalence classes. You can mess around with the set of elementary inputs. You can provide your own adversarial inputs and see what sort of numerical discrepancies you can discover. Thank you.
Okay, I guess I can clap for all the audience. Thank you for your talk.
Thank you.
We have a number of questions. One is about this, the way that you identify different implementation of the same functions. You give them these base inputs, I believe you call them, and then you check their output. So the question is about the manual checking that can be done for that. How hard was that manual classification? And does one even need the full automation there?
Yeah, that's a great question. So the process of identifying function synonyms manually involved, it was very laborious. It involved consulting documentation, looking through source code, performing our own experiments. So big kudos to one of the authors on this paper, Shun, for taking on a lot of that manual work. And the reason for automating this process would be an ease of adding new libraries to this pipeline. So more libraries means larger equivalence classes, which means a better consensus when performing the differential testing, potentially. And so it just makes it a lot easier to automatically discover those function synonyms rather than going through every function that you find and including it. And also could provide a means too for expanding the scope of this as well more easily.
Okay, thank you. While waiting for the audience, let me ask one of my questions. Lingming Jiang is thanking for your answer. When you search for these equivalence classes, is it only exact equivalence? or do you look for some relations among functions? For example, maybe one returns, say, r squared, the other returns r. Also, what about the types? Maybe one returns a long, the other returns double. How much precision differences do you allow there?
Great question. So to the first point, so we discuss this further in the paper. We provide a rigorous definition for what function synonyms are, but briefly, like take an example like an nth root and a square root. We don't define those to be function synonyms because only one can be used to test the other differentially, but the other one, so in other words, the functionality of one is a subset of the other. And so we define them as being an equivalence relation between functions rather than just a binary relation, with a few caveats here and there, but again, a full discussion in the paper. And then with respect to data types, so this is an area for future work. In our case, for instance, for C, we just, or for GSL rather, we just took all the functions that had doubles as outputs, and that fit for this library, but for our particular scope. But interesting future work could be to include those that have arrays, for instance, as output types, and include linear algebra into this. I think that could be very fruitful, potentially.
Okay, thank you very much. There are a few more questions on Slack. I guess you can follow offline. We should not fall behind the schedule. So let me thank you once more, and maybe we can start with the next talk.
Darko, thank you very much.
Okay, please follow up on Slack.
Yeah, we'll do.
Okay, the next talk will be testing high-performance numerical simulation programs, experience, lessons learned, and open issues. This will be recorded video, but Xiaohe is here to take your questions. Please type your questions into Slack. Yeah, you can start the video. Thank you.
Hello, everyone. I'm Xiao. I'm very glad to present our paper, Testing High-Performance Numerical Simulation Programs, Experience, Lessons Learned, and Open Issues. This paper focuses on the testing of a particular sort of programs named high-performance numerical simulation programs. These programs are used to simulate complex real-world systems on high-performance computers according to mathematical and physical models. They play a crucial role in modern science and engineering. For example, the formation mechanism of 100 disclosure loops, which was regarded as a 50-year-old radiation damage mystery, was revealed based on large-scale molecular dynamic simulation. Our work is based on a national R&D project whose goal is to create a virtual reactor, a system that is able to achieve the multiphysics and multi-scale simulation of a reactor core to support the design and analysis of a nuclear power plant. For instance, if we need to know how thick the wall of the core should be built, we can ask the virtual reactor to do some complex simulations. Assume that the simulation results tells that 10 meters are solid enough to protect the reactor, and based on this result, we build the reactor. But what if there's a bug? Obviously, high-performance numeric simulation programs must be systematically verified, and that is my job in this multidisciplinary project, led by domain experts. The goal of this paper is to present our experience of testing the simulation programs of virtual reactor. For better discussion, we set up 4 research questions. RQ1 is about the testing approaches. RQ2 is about the test inputs. RQ3 concerns test oracles. And RQ4 considers the bugs. The basic information of the programs under test is listed in the table. There are 5 programs, namely ANTMOC, MISA-MD, MISA-SCD, MISA-RT, and SYNTA. The 5 programs cover different application domains, such as neutral particle transport, molecular dynamics, and cluster dynamics. They vary in their size and programming languages. In general, they have many parameters and produce complex outputs. The common structure of the program under test can be depicted as this picture. They usually consist of a pre-processing module, a main calculation module, and a post-processing module. The programs have some characteristics. First, the computation pattern is generally a loop. Second, the entire computation, even deployed on a supercomputer, may require thousands of core hours. Third, the computation may be stochastic. Fourth, the computation is by nature inaccurate due to the multi-level errors, such as inaccurate input, imprecise physical and mathematical models, and floating point arithmetic. Finally, the programs have complex input and output. They have lots of parameters, and a single parameter may also be an external file that describes the geometric shape and the metal material. Moreover, the output may contain several gigabytes. We followed a very natural work procedure to test the 5 programs. First, when developers regarded that their program was ready for testing, they sent the program to us. Then, we collect possible test inputs and oracles and test the program collaboratively with developers and domain experts. If the program fails the test, then we ask the developers to fix the program and rerun the test. We tried several testing approaches, including classical testing, differential testing, property-based testing, metamorphic testing, retrogressance extrapolation. We will discuss them later. And this table summarizes the total numbers of test cases, properties, and metamorphic relations that were used to test the programs. You can see that we suffered from a shortage of test cases and severe oracle issues. And this table summarizes the numbers of bugs we found by adopting our approach. In total, we found more than 33 bugs. Please keep in mind that this project is mainly dominated by domain experts and HPC experts. We worked under the pressure of time, budget, and resources, and the project leader. We are not allowed to fully explore all the possibilities as we usually did in the study of software testing. Now we'll begin to introduce the details of applying our testing approach. First, let's consider the classical testing. To apply classical testing, we need a test case that contains both the input and expected output, and then check whether the actual output is equal to the expected. We applied classical testing to 4 programs. However, we only developed 12 test cases in total, which are obviously insufficient. Regarding checking the output, we also encountered some difficulties. For example, for Antmok, we can only check whether the actual output is close to the expected, since it's never equal to the expected output. For MISA SCD and MISA RT, we can only do wither comparison because the expected outputs were presented as figures in literature. For SYNA, we can only ask the domain expert to check the result, because the expected output is confidential. To apply differential testing, we check whether the actual output of the program under test is equal to that of a comparable program. The major difficulty is that not all the programs have fully comparable versions. For example, for Antmok, the open source program OpenMOC is only partially comparable because it does not support fast reactors. We found 9 bugs by using differential testing, and SYNA contributed 7 of them. Because SYNA is a rewritable function program FRAPCON, we are able to verify every function in SYNA. To apply property-based testing, we need a property P and check whether P holds for every input and the corresponding output. The key is whether we can define effective program properties. The properties may be derived from physical models. However, it is too difficult for us to do so due to the lack of mathematical skills and the domain knowledge. The properties may also come from the program implementation. Such kind of properties are easy to define but may be ineffective to detect bugs related to numerical algorithms. In practice, we defined 17 properties in total. You can see that all the properties are very simple, but they helped us find 18 bugs. Metamorphic testing is an innovative testing approach that is developed from the property-based testing. The basic idea is to use a metamorphic relation R, which is a necessary property, to check whether a source test case and a follow-up test case can make R satisfied. Similar to property-based testing, the key to metamorphic testing is to define high-quality metamorphic relations. We encountered the same difficulties as we faced in property-based testing, but the situation is worse. We find that the metamorphic testing is much harder to be understood by domain experts and HPC developers. However, without their help, we cannot identify good metamorphic relations. In our practice, we identified 10 metamorphic relations. Here are some examples. You can see that these metamorphic relations are very domain-specific. The 10 metamorphic relations helped us find 8 bugs. Richardson's extrapolation was proposed by the scientific computing community and was used to verify many numerical algorithms. When a program has a step size h, the following equation must hold. The equation is a very strong mathematical property, and it is very sensitive to bugs. It can be viewed as a special metamorphic relation. However, this approach has low applicability. It requires that the program's math model follows a certain format. We find only MISA-RT and Athena satisfy this requirement. Besides, the approach doesn't provide rich information for debugging. So although MISA-RT failed the test, we don't know the reason until now. Finally, we also find that the equation may not hold if the implementation does not strictly follow the math model. However, the deviation is possible and common, for example, due to performance optimization. Now, let us consider our research questions to summarize our real experience. Our first question is what approaches are applicable and effective. We tried 5 testing approaches in our practice. Generally speaking, property-based testing and metamorphic testing are 2 most applicable and effective testing approaches. The main difficulty is that the 2 approaches are not very easy to be learned, especially by domain experts. Consequently, defining program properties and metamorphic relations becomes more challenging. However, even with simple properties and metamorphic relations, we still found many bugs. Hence, we recommend these 2 approaches. Regarding other barriers, the scalability, the portability, and support for multiple programming languages cannot be neglected. Many program analysis and testing approaches cannot be used due to the scalability reason. For instance, we tried to use FPDebug, a dynamic floating point error analysis tool, to examine our programs. However, when FPDebug is turned on, the program becomes around 400 times slower. Since our programs may require thousands of call hours to return a result, FPDebug cannot be used in this situation. Portability is another issue. Our programs are usually run on a supercomputer, on which most existing software testing tools cannot be used. Our second question is where we can find test inputs. In our practice, we collected test inputs from domain benchmark problems, existing programs, literature, and experimental data. However, there are some pitfalls for our source of test inputs, so in general, we suffered from a shortage of test inputs. For example, if we want to reuse test inputs from LAMPS for MISA-MD, we have to do some non-trivial conversion due to the difference in input format and parameters. You may also wonder whether we can randomly generate new test inputs. Our answer is it's possible, but also difficult, because there may be some complex domain constraints over parameters. For instance, in MISA-SCD, CO is a value between 0 and 1. It refers to the copper content in an alloy. If it is increased to a certain threshold value, then the alloy may become not salt, and many other parameters must also be adapted. The third question is what kinds of test oracles are there? First, we use numeric values as test oracles. However, because our programs are by nature inaccurate, the program outputs never match those values. A simple alternative, called oracle approximation, is to determine an error bound. However, how to define such a bound is another form of the oracle issue. We also used comparable programs as test oracles. However, when our program is different from the comparable program, there's always a dispute about which program is correct, because the comparable program may also be wrong. Video results are frequently used as test oracles. It is a common practice in numeric simulation. Video comparison is inevitable because in many papers, their results were only presented in pictures. However, video comparison requires extra post-processing efforts and lacks automation. Domain experts often play a role of test oracles. we sometimes ask them to manually check whether the actual outputs were correct. However, their opinions are not always reliable. Different domain experts may also give inconsistent opinions. Necessary properties are also test oracles. As we have explained, it's very hard to derive necessary properties. Please look at this math model of MISA SCD. It is completely out of our ability to interpret, analyze, and derive any property or metamorphic relation. The last question concerns bugs. In our practice, coding errors are the most frequent bugs. ISSTA contributed 11 of them. ISSTA is a rewrite of Frapcon, which was written in Old Fortran language. Many bugs can be attributed to the misunderstanding of the old code. After that, there are also many bugs in preprocessing parallelization and algorithm implementation. This implies that special attention must be paid to find those bugs. We found only one numerical error, but it is probably due to the lack of scalable tools that allow us to conduct systematic testing. Based on our experience, we propose the following test strategy. First, apply differential testing to compare put and its sequential version to find parallelization errors. The consistency between the sequential and the parallel version is also very helpful for debugging, since parallel programs are much harder to be debugged. Second, apply property-based testing and metamorphic testing to verify put because the two approaches are very applicable and effective. Third, if a comparable program P' is available, test put by comparing with P'. Finally, validate put with domain benchmark problems to address domain experts' concern. The last step is essential because domain experts usually value those domain problems highly. Another important lesson is that domain experts must be involved in testing. A very bad practice is to ask the necessary information from domain experts and then do it yourself. The problem is, much detailed domain knowledge about put may not be provided because domain experts do not know what information is necessary for testing, and neither you know. A good practice is to keep domain experts along with you forever. Since they are your boss, they may not want to help you. So probably the best practice is to become a domain expert yourself. We also notice that the use of put influences its testing. So make sure that you already know the intention of put before testing. Our last lesson is that we should preserve and manage the actual test outputs seriously. There are many benefits to preserve actual test outputs, although it may require a lot of storage. Based on our practice and observation, we also identified a few research suggestions. First, how to analyze and test a program in a context of multi-level errors is an interesting topic. As we have explained, there are many errors that may lead to an inaccurate result. When the program output is inaccurate, how can we know whether it is due to a bug in the program or an error in the input data? There is also urgent need for adapting existing or developing new testing techniques and tools for high-performance environment. However, doing so is non-trivial and challenging. We have to consider many practical factors, such as multiprocess and multi-thread execution, some special restrictions on supercomputers, and compiler friendliness. Third, in some domains, such as neutral particle transport, domain experts heavily rely on benchmark problems. However, from the perspective of software testing, those problems are very limited, and it's unclear that whether they are effective to detect bugs. Further studies on the development and assessment of domain benchmark problems must be carried out. Here comes the end of my presentation. Thank you for listening.
Okay, thank you for the presentation. It was very insightful talk. Let me see, the questions may be arriving from the audience. Maybe I can ask one of mine first. Found this point very interesting about domain experts, that they struggle to understand metamorphic relation. So what is the background of these domain experts? You mentioned they're not always reliable. They may even have inconsistent opinions among themselves. Are they physicists? What is their background?
They are computational physicians. They come from the community of computational physics or computational materials. So they have a few knowledge about programs. So because they also write some program, but their main background is about physics and material.
Okay. Okay. Good. Another question is about these executions for the simulation. So when you run the actual big, large simulation they run, you need a big, large supercomputer. But what about your tests? Kind of in your examples, when you run that put of I1, I2, I3, how long are those executions? Did you find bugs with very, very short executions, or did you also need to run for hours and days in order to find bugs?
For some programs such as MISA RT, we do run very short tests because the program is relatively simple. So it can return a result in a very short time. But for other programs, we run it on our cluster or even on a supercomputer because they require a lot of execution times. And another issue is due to the limitation of due to the lack of test cases or test inputs. We can only use in most cases we can only use such as the domain benchmark problems. They usually require very long execution time. Okay. So in most cases we run the test on our own cluster, but for some tests we do run on a supercomputer because all the program has to be tested on the supercomputer.
Okay, but eventually when you find the bug by running on supercomputer, when you make
it may require several weeks.
Okay, so you're saying even when they map back and debug, this turns out to be the only or the smallest inputs that can expose that bug. Even eventually when they debug, they cannot construct a smaller input to show the same bug, can they?
I think that's a very interesting question because our developers do face such difficulties, and I think we need more investigation on this topic. How to simplify the input from a very complex one.
Okay, thank you very much. There are a few more questions on Slack. If you want to follow up, let me clap to thank for the audience.
Thank you.
I cannot all clap. We have to continue. Let's go on to the next talk. This will be functional code clone detection with syntax and semantics fusion learning. This will be given by Zishi. Also, let me point out, this one did win a number of things of these artifact badges, artifact evaluated, artifact available, and artifact reusable. So please go ahead.
Hello, everyone. Can you see me? Can you hear me?
See the slides. We can hear you, yes.
Okay. Good afternoon, everyone. I am honored to be able to participate in the ISSTA meeting. Today, the title of my presentation is Functional Code Clone Detection with Syntax and Semantics Fusion Learning. I am one of the authors of this paper, Zixi Liu, and I am from Nanjing University in China. And below, I will officially start introducing our paper. The topic of our paper is code clone. Code clone detection is substantial in software engineering and has been widely studied. If a defect is defined in a code snippet, all the clone code snippets need to be checked for the same defect. First, I want to briefly introduce the code clone detection, which is the main task of our paper. Code clone can be divided into 4 types according to different similarity levels. The code snippet in the upper left corner is an original code, and the other 3 code snippets are clone examples of type 1, 2, and 3, respectively. In these figures, there are some underlined parts. They are the differences from the source code. The type 1 clone can be understood as exactly the same code snippets. As you can see in the figure, 2 additional comments have been added to the type 1 clone sample, and the other comments have not changed. The type 2 clone can be understood as renamed code. As you can see in the figure, the types of variable s and p have changed from float to int. Type 3 can be regarded as almost identical code snippets. In the figure, in addition to changes in variable types and comments, some statements have been deleted. That is, the functionality of type 3 code clone may not be the same as the source code, but they are quite similar. Our proposed method mainly used to solve the type 4 code clone, that is functional code clone. Functional clone detection means that the structure and the syntax of the clone code pair are very different, but the functionalities are the same. It is the most complicated clone type because the syntax and the syntax of the source code are flexible. Many approaches try to use syntax-based or semantics-based information to represent the source code.
Sorry, just a second. Your slide is back to number 1. It's not in the presenter mode, at least for me.
Can you see this?
Yes, you're back to fine now. Please go ahead.
Let's first take a look at the syntax-based code representation. Usually, we use abstract syntax tree to represent the syntax. It is a tree graph that defines the structure of the source code. The AST has been used in many approaches in different program analysis tasks, such as code clone detection, program translation, and automatic program repair. Another commonly used semantics-based representation is PDG, that is Program Dependencies Graph. PDG is a graph notation that contains both data dependencies and control dependencies. The figure shows the PDG corresponding to this program fragment. The dotted line and the solid line represents the data flow and control flow, respectively. As you can see, just a simple for loop will introduce a complicated graph, and the directed connections are also intricate. Since it is so complicated, analyzing the PDG and semantics representation has limitations in large-scale procedures. In summary, existing approaches have limitations in detecting functional code clone. On the one hand, although AST can represent the abstract syntax of the source code, it is not able to capture the control flow between statements. On the other hand, each node in PDG is a basic code block, which is too cross compared with AST. The improper gravity may lead to the lack of details inside code blocks. Besides, AST is commonly used to represent a method, while PDG is used to represent an overall file. Thus, most existing approaches capture code similarity and the gravity of a single method or a single file. To improve the existing approaches, we detect functional code clones through syntax and CMAX fusion learning. As can be seen in the figure, we use AST and CFG to represent the synaptic and semantic features, respectively. Such a fusion code representation can describe the code. Our proposed approach consists of the following 3 components. The first one is identifying the functionality with the crawl graph. The second one is extracting syntactic and semantic code representations. The last one is training a DNN classification model. Next, I will detail the design of each part. We first extract crawl graph to identify the functionality.
Sorry, the slides are again off. I don't know what happened. It's again not in the presenter mode. Sorry about that, but I think it's better to get it back.
Oh, I'm sorry. Can you see now?
Yeah, it's fine.
We extract the crawl graph to identify the functionality in each source code file. There are some basic crawl graph examples in the lower left corner. A directional arrow indicates that one function calls another function. We regard such functions with call relationship as an entirety, responding functionality. In the subsequent analysis of the CFG, we connect CFG between the functions and that have a calling relationship, as shown in the diagram on the right. The method B and method C on the right side of the dotted line have a calling relationship, and the CFG after connecting them is very similar to the method A, which is on the left side of the dotted line. In fact, these two corresponding source codes achieve the same functionality. So we use the CFG to represent the control flow for a single procedure and use ICFG to represent control flow for a program. After identifying the functionality of the source code, we extract the AST as the syntactic representation and the CFG as semantic representation. We first extract the AST of each method and obtain the corresponding identifier sequence by traversing the AST tree in pre-order. Meanwhile, since the variable names can have an effect on functional code clone, we normalize the identifier sequence by replacing the variables by its type, such as int, double, char, and string. Then we apply word-to-vector, a word embedding technique on each identifier. The syntactic feature of
sorry, Zishi, the slides are again broken. Maybe when you click on the next one, please click on something else. I will try not to interrupt anymore, but they go back into non-presenter mode.
As for semantic information, we extract the CFG of each method. It is a directed graph that with a set of vertices and edges. Then we apply graph to vector, a graph embedding technique to generate the corresponding feature vector. For the method with core relationship, we first connect the corresponding CFG, which has been explained before. Then we apply graph to vector on it. We propose to use a deep learning model that can effectively detect functional code clone between code snippets. The architecture of the DNN model is shown in the figure, which consists of 4 components. First, we obtain the syntactic and semantic feature vectors and concatenate the 2 vectors together as the input of the model. The syntactic and the semantic vector are both represented as a 16-dimensional vector. We choose this length through experimental comparison, and the experiments will be shown in the later. We use a pair of code features to represent whether the 2 functionalities are clones, and the label is 0 or 1, meaning the code pair is cloned or not cloned. There is a fully connected layer. It is to avoid the effect of the fusion features order. Then, with the hidden layer, use linear transformation followed by a squashing non-linearity to transform the inputs into narrow nodes in the binary classification layer. Finally, there is a softmax layer, which converts the functional code clone into a classification task. In order to verify the effectiveness of our approach, we designed a series of research questions, and then we try to answer them through experiments. This page shows our experimental settings, where I want to highlight the dataset we use, OJ clone. It contains 104 programming tasks, and each task contains 500 source code files submitted by different students. For the same task, the code files submitted by different students are considered as functional code clones. Such a dataset is very suitable for functional code clone detection because the structure and the code must be different when different programmers implement the same functionality. This dataset is also widely used in the research of existing code clone detection, which is convenient for us to compare with our tools. And the first research question is that how does our approach perform in functional code clone detection comparing to the state-of-the-art approaches? We compared as many existing clone detection tools as possible, mainly in terms of accuracy, recall, and F1 score. In addition, we also compared to the training time and the prediction time of each method. The results are shown in the table. As can be concluded that CD, LH, DeepSim, ASTNN, and our approach have the ability to detect functional clones, and our approach achieves the highest F1 score among all approaches. Compared with ASTNN, our approach achieves higher recall at the sacrifice of a little precision. This is mainly because our approach leverages both syntactic and semantic information in functionality gravity. As for the training time, Deckard and Social CC do not need to train the model and conduct code clone directly. DLC implicates a simple deep learning model which costs much less time. Compared with other deep learning-based approaches, the training time of our approach is much shorter. Thus, our approach is more efficient. And the second research question is that how does the fused code representation perform in functional code clone detection? We arrange the three features of text, AST, and CFG. The compared results of each cases. The compared result of each cases. The text feature is that we treat the source code as text and apply word embedding technique to represent the source code. As the results shown in the table, our proposed approach, the fusion of AST and the CFG, can detect functional well, and it achieves the highest recall and F1. The fourth combination.
Slides again.
The fourth combination, which uses only text features, combines the best accuracy but the lowest recall rate and F1. Although text features achieve the highest precision, it is still not usable. When we use all three features, the result works well, but a little worse than our approach. We get too much information and too strict requirements will introduce the recall, while improve a little bit of precision. The third research question is that how does our chosen embedding techniques perform in functional clone detection? We evaluate this problem from two perspectives. On the one hand, we compared the comparison of different word embedding and graph embedding techniques. The results are shown on the table on the left. It turns out that the word-to-vector and the graph-to-vector is the best combination. On the other hand, we compare the effect of different vector lengths on the results. We use the vector lengths of 8, 16, 32, and 64 for experiments. The data is in the table in the lower right corner. The graph on the upper left shows the visualization effect. As can be seen, the longer vector will increase the training time with very little increase of F1, and the shorter vector cannot capture sufficient code features. The last research question is that how does DNN perform in functional code clone detection compared to other traditional machine techniques? We compared with SVM logic regression as traditional machine learning techniques. The results can be found in the table. Obviously, our approach performs better than the traditional machine techniques because our approach can better capture the hidden features from the fusion vector. Now, I'd like to make a conclusion for my representation. We have presented a novel approach to detect functional code clones with SyntaxBased and CMax fusion learning. And we built a deep learning model that can convert code clone detection into a binary classification problem. The experimental results show that our approach achieves a significant advance over state-of-the-art approaches in terms of the F1 value, and it has a good detection efficiency after the model training. Thank you for your listening. If you have any questions, please feel free to ask. Thank you.
Okay, thank you for your presentation. Let's see, for the questions, I hope that more people can type something in Slack. Meanwhile, let me ask one of my questions. So your evaluation mostly focused on precision and recall with respect to some ground truth. I did not always follow how you get that ground truth, but I wanted to say something that the clone detection may be viewed as a foundational analysis that something else then applies. Maybe my security analysis use that, or my bug finding, or whatever else. There is some client that uses the results from the clone detection. So did you evaluate with any such client, or how important do you think that these differences may be for a client analysis?
I assume this is something about the data set. We use the data. We conduct our experiments on the OJ clone data set. It is actually the students need to provide their source code to solve the same task. So different students solving the same task. So the source codes between them are functional code clone. We assume that they are functional code clones. And as for the RQ1, we compare them on the same data sets, the OJ clone data sets. So this is my answer.
Okay. That's fine answer. I guess mostly addresses the part on ground truth, not necessarily about client analysis, but we can follow the client analysis on Slack later. I want to ask about the ground truth. First, you said that these students submit about 500 files. That looks like a rather big answer. I'm not sure if our students write 500 files throughout their education. So how did these students get 500 files?
There are 5 different versions of the source code file. It is they are all committed by different students, and we assume that the 2 source codes from same task is functional code clone, and if a code is to solve task 1 and another code is to solve another task, we assume that these 2 codes are not functional code clones. And we will produce 1,000, 10 million code clone pairs and another non-code clone pairs.
I see. Okay. There is 500 files total across 100 students. Not each
Yes.
student has 500 files. Okay.
Yes,
That explains
yes.
it more. Sorry, I was confused about that point. My related point to that is about the bugs. What if some students have bugs, and then the 2 versions are not actually functional equivalent? One may be wrong and incorrect. And maybe my task as educator is to find something like that, find which submissions are buggy, or find potentially which students may have copied from each other. This may be kind of the client analysis that I have for clones. As a professor who has 2 great students, I don't care if they have clones as such. I care, did they copy from each other or not, or who has a bug or doesn't have a bug. So did you evaluate for something like that?
Yes, we consider that. All these source code are open sourced, and it is the online judge system. So each student actually they solve the same task, and we can verify it. They solve the same task, but we can't guess whether they are copied each other. This is we can't know. But we did our experiment on our data set. We created ourselves. The results are the same. So we think the OJ clone data set is students. They didn't copy the same source code.
Okay, fine. Still the question remains, how do you know whether some is buggy or not? But maybe we can take that offline on Slack. We should get going to not fall too much behind. Let me clap to thank you for the presentation in the name of our entire audience.
Thank you for listening.
Yeah, please follow up on Slack. So let's go on. So our next talk will be learning to detect table clones in spreadsheets. And this will be given by Yakun. So please start.
I'm Yakun. And I will share my screen. Can you see the slide, or can you hear me?
Yes, we can see and hear you.
Okay. Hello, everyone. I'm Yakun Zhang from University of Chinese Academy of Science. It's my honor to be here and talk about our work learning to detect table clones in spreadsheets. Spreadsheet systems are one of the most successful end-user programming platforms and have been widely used in variety of business tech, including data storage, data analysis, financial report, and so on. Similar to code reuse, end users often reuse existing spreadsheets to speed up their development productivity. For example, Alice wants to write a financial report. She firstly searches some similar report, and then copy-paste and revise some data and formulas. Finally, she can easily get a new report. The two spreadsheets excerpted in the previous example are two tables. A table is a rectangular block of cells and prescribing certain business tasks. For example, this table is for storing and analyzing the working hours in January. A table usually has 4 elements, such as headers, data, formulas, and cell formats. Table clone is two tables which share the same or similar computational semantics. Let's take a look at this picture. The two tables are analyzing the working hours for 6 people. And then they have the same headers, similar formulas. According to this information, we can know that they have similar semantics and form a table clone. However, the reuse process are not records that the two tables were created by copy-paste modifying in the spreadsheet system. Therefore, it's really hard to do the spreadsheet analysis related to table clones. So it's really important to detect table clones in spreadsheets. Actually, table clones can help to detect errors. In a table clone, its corresponding cells usually share the same or similar computational semantics. The inconsistent among the corresponding cells usually indicate errors. For example, cell E7 in the top table and cell E6 in the bottom table should have the same computational semantics. However, they contain inconsistent formulas. Based on this observation, we can use table clones to detect spreadsheet errors by analyzing their inconsistency. Besides this, table clones also help for data integration. Table clones are usually used to perform the same or similar business tasks. However, these related tables usually scatter in many spreadsheets. We can integrate all related tables in a table clone and form a table summary. After that, table clones also help for table template extraction. We cannot extract table template from only one table. Table clone provide a pair of instances, and we can extract a template from them. We observe that the tables in a table clone can be modified in different ways. We categorize the table clones into 4 types. The type 1 clone is identical table which allow variations in formats. This is an example of type 1 clone. They are identical in content, but variations in background colors. The type 2 clone have variations on data and formulas, and also variations in type 1. As the figure shows that the differences between two tables are data and formulas. Actually, they form a type 2 clone. The type 3 clone have variations on table headers, and also variations in type 2. The example shows that the tables have variations in row headers compared with type 2 clone. The type 4 clones have variations on rows or columns and also variations in type 3. As you can see that compared with the two tables, they change rows and columns. Among the 4 types, type 1 and type 2 have without changing structures. However, type 3 and type 4 have changed. The existing approach can only detect clones without structure change. The first existing approach is data clone, which is to identify 2 blocks of numerical cells with almost the same values. As the example shows that this approach finds 2 parts which contain same numerical cells as their clone area. And this approach can only detect type 1 clone. The second existing approach is table check, which is to identify two blocks of numerical cells with the same headers. As the example shows that this approach firstly detects same headers and then find the clone parts. Actually, this approach can only detect type 1 and type 2 clones. Our goal is to automatically identify all types of table clone in spreadsheets, especially for structure change table clones. We observe that although some of table clones contain variations, they also share similar structure and formats. For example, the table clones share the similar headers, similar formulas, and similar formats. Let's take a look at our approach overview. Given some spreadsheets, LTC first identify tables and then enumerate table pairs for each two tables. LTC extract 12 features about the structure and format for each table pair. Finally, table clones are predicted by leveraging a binary classification on feature similarity. Next, I will explain detail of our approach. In the first step, LTC need to identify tables. Firstly, we identify block according to empty lines. So we put the spreadsheet into 3 blocks. However, a table can be separated into multiple blocks by empty lines. We observe that in a table, different blocks share the same row or column headers. The headers usually located in the top and the left of the table. You can see that the first block and the second block share the same column headers. Actually, they belong to a table. We merge blocks with the same headers as a table. The third block has its own headers and can form another table. The second step is to select features and calculate the similarity of corresponding features in the table pairs. We observe that the clones always have similar structure and formats. We'll select structure features such as column headers and row headers. Taking column headers as an example, we denote column headers as a set H1 and H2, and the similar calculation SimF1 shown in this slide. According to this formula, when the two tables have the same column headers, the similarity score is 1. However, if two tables have no common column headers, the score is 0. We also select formula features as our structure features. Formulas in the corresponding cells among table clones often have different expression in the A1 format, but the same expression in the R1C1 format. We firstly gather R1C1 format. And then we divide R1C1 formula into 2 parts, such as operators and parameters. Firstly, they have the same operator sum. Secondly, they have 2 same parameters. This is a corresponding similarity calculation formula. We can see that the 2 formulas share the similar computation. Format information is also the important feature. We select font colors as a format feature. You can see that the font color of cell A1 is red and the font color of cell B1 is black. We analyze all cells in a table and summarize the information. For each table, we build a keyframe quiz list of key count to do the summary. And the similarity calculation are as follows. In this formula, the red part denotes the frequency difference for a type of font colors. And this red part denotes the frequency summations for a type of font colors. Actually, more cells in 2 tables share with the same font colors, the higher similarity score we can obtain. The total 12 features are shown in this table. The first 4 features are structure features, and the last 8 features are format features. Note that we don't consider data cell value as a feature because the values cannot usually reflect the computational semantics of a table. For two tables in a table clone, they usually store different values. The third step is to identify table clones. We firstly need a group of table clones and non-clones as our training data. We extract features and calculate the similarity through them. And then we need to select a binary classifier. According to our experiment, when we use random forest algorithm, LTC can obtain the best performance. After we choose a suitable classifier, it can predict the clone result. To evaluate our approach, we raise three questions. The first is, how effective is LTC in detect table clones? The second is, how is LTC compared with existing technologies? The third one, is LTC robust on different data sets? Because there is not such training data for table clone detection, we firstly build a ground truth for this approach. We select EOCs and Aaron Cobra as our experimental subject. We then started to sample spreadsheets. We randomly choose a spreadsheet from the corresponding corpus and inspect whether it contains table clones. We then sample 50 spreadsheets from EOCs and 50 from Aaron and label table clones and non-clones from them. The statistics of ground truths are shown in this table. We total label 615 table clones and 10,215 non-clones in the 100 spreadsheet. To understand the distribution of table clone types in the ground truth, we make a bar chart. As the bar chart shows that 58.5% of table clones involve structure change. As for experimental design, we randomly select 35 spreadsheets in the EOCs and 35 in the Aaron from the ground truth as a training set. We use the 416 table clone in the 17 spreadsheet as a positive samples, and the 8,122 non-clones as the negative samples. As for testing set, we use the remaining 190 table clones to evaluate. After understanding the structure of our ground truth, we started to evaluate our approach. We first use LTC to identify table clone in the test set, and the precision is 97.8%. This shows that LTC effectively detects table clones. For the second question, when compare LTC with table check on their table clone detection capability, we test the table check in the same test set, and the results are shown in this figure. Through the figure, we can see that LTC significantly outperforms table check in table clone detection. This is partly because table check can only detect table clones with the same headers, such as type 1 and type 2 clones, but cannot detect type 3 and type 4 clones. Note that we don't compare our approach with data clone, since this is totally different from table clone. The third question is to validate whether LTC is robust on different data sets. We randomly choose 100 spreadsheets from EOCs, Aaron, and FUs respectively. We apply LTC to detect table clones within one spreadsheet. We call them intra-spreadsheet clones. It's really challenging to manually validate all detectable clones. Thus, we randomly sample 100 spreadsheet table clones from each corpus. And the results are shown here. Furthermore, we also apply LTC to detect the table clone among spreadsheets. We call them inter-spreadsheet clone. And this is the result. Through the table, we can see that LTC can detect both intra and inter-spreadsheet table clone precisely and is really robust on different corpora. In summary, we first propose a commonly used rotation in spreadsheet, table clone, in which two tables share the similar computational semantics. We then propose a learning-based approach, LTC, to detect table clones with or without structure change, by exploring the structure, form, and the format similarity among the table clones. Finally, we implement LTC and evaluate on real-world spreadsheet. The experimental results show that LTC can detect table clones with high precision and recall. That's all. Thanks for your attention.
Thank you for your presentation. See any questions from the audience? I understand it's getting late, third day among the last sessions. We still have one more on tools. No questions. I can go with some of mine. Maybe let me first start from what I wrote the last. I understand it's not directly about your work, more about the motivation, about the whole problem. But what are the common bugs in spreadsheets? How many of these bugs are actually due to clones?
I assume the question is about our evaluations are performed with precision and recall, and my answer is that there are three evaluations, and the first evaluation is to detect whether our approach is effective, and the performance is precision and recall, because our goal is to automatically identify table clone, and we focus on how many the real world table clones can be detected by our tool, and how many real world table clones cannot be detected by our tool, and this is our focus. And the second one is to compare it with the existing table clone tools, and we call them table check. And we also compared with them in the same data set, and compare with them the precision and the recalls. And the second evaluation is to evaluate whether our approach can robust to evaluate in different corpus. And we also evaluate our tool into different corpus, and within one spreadsheet and among the spreadsheet. And this is my answer.
Okay, fine. I guess you've answered the question one. Let me know if you want me to repeat some questions or to go a bit slower. It's good that you are finding this precision and recall for potential clones. But did you try to evaluate whether some people would view these as real bugs? Do you try to talk with users and say you have a wrong clone or you have a good clone, or to get some feedback like that from the people who actually prepare these spreadsheets?
I assume the questions about it's about whether precision and recall can evaluate our approach, and whether the precision and the recalls, just like me says, the real table clones are we can detect the real table clones, and we cannot detect the real table clones. Actually, the judge is from the human beings. We invite two volunteers, which are two master students, and the fourth author are to evaluate to make a data set, and this is our ground truth. And the data set shows that well, in this spreadsheet there are so many table clones, and the table clones are showing here, and we run our tool, and we compared our result with the ground truth.
Okay, Fine. There are a few more questions in Slack. They're written there, so if you want to follow up there. I guess this concludes then our session. Let me clap for this talk. Thank you for your presentation. Thanks to all 4 speakers. We're going to have a short break now, and then there will be 2 demos in about 15 minutes from now. So see you then. Thank you, everyone.
Thank you.